right, so we have a cold air standard Otto cycle, and it's in English units, so we just have to be really careful about those units. We're given the maximum temperature, which occurs after that constant volume heat addition process, so the maximum temperature is at state 3. And then we want to find the little work net out in BTU per pound mass, the thermal efficiency, and the mean effective pressure in PSI. And for cold air standard assumptions, if we're taking this at room temperature, which unless otherwise specified, cold air standard is going to be at 25 degrees Celsius or 77 degrees Fahrenheit. But I could pull those CV and CP values out for air, and I believe that's in table A19. You're going to have to interpolate between 40 degrees Fahrenheit and 100 degrees Fahrenheit to get those values. On a test, I would give you those. I wouldn't require you to take the time to interpolate, but just FYI, that's where those values are found. And now I'm ready to get my governing equations and start solving my problem. So little work net out, we've seen before that this is just U3 minus U4 minus U2 minus U1. And because I'm making cold air standard assumptions, I can put those delta U's in terms of CV delta T's. And then my thermal efficiency, well, I've got the numerator part of that. I've already got that in the first governing equation. And then my Qn occurs between 2 and 3, so that's going to be U3 minus U2. And since I'm making cold air standard assumptions, those delta U's become CV delta T's, and you could cancel those CV's out if you wanted to. And then my mean effective pressure, I've got the numerator part of that, and then I can kind of rearrange the denominator part to get it in terms of just the specific volume and the compression ratio. All right, so I'm ready to start plugging numbers in and figuring out what all those temperatures are. And I am going to need to, I know the temperature at state 1, but I am going to need to figure out what the specific volume is at state 1. So the specific gas constant, in SI units, I always remember it's 0.287, but I can't ever remember what it is in English units. So I'm going to go ahead and calculate what it is. So your specific gas constant, by definition, it's equal to the universal gas constant divided by the molar mass. And that molar mass, you can find that in, you can find it in table A1. So for air, it's 28.97. Pound mass per pound mole. So it's in table A1E. I should have said that. I'm sorry. 28.97. And the R bar is found at the very bottom of your conversion factors. There's several different units for universal gas constant. I just happen to choose 1545 foot-pound force per pound mole degree Rankine. So it looks kind of ugly, but it's okay. Everything will kind of pretty up in just a minute. And of course, my temperature is in absolute temperature units. I do need to make sure that I reconcile all my units, and I get a specific volume of 13.35291. Of course, I'm not rounding that off until the very end. But I do kind of look ahead and I see that mean effective pressure is going to need to be in pound force per inch squared. So I'm going to go ahead and put this guy in terms of inches cubed per pound mass. So it's a bigger number, obviously, but I'm going to go ahead and keep that in my back pocket, see which one is useful to me when it comes to plugging in those numbers. And now it's time to go on to state 2. So I know from state 1 to state 2, I've got an isentropic compression process for an ideal gas. So I can use an isentropic relationship for an ideal gas, assuming constant specific heats. So I don't need to use my ideal air tables in A22E. I just directly calculate what T2 is. So I know V1 over V2 is just the compression ratio, and I directly calculate what T2 is. Once again, not rounding off until I plug in all those numbers into those governing equations up there. Oops, there's that equation. All right, and now I'm ready for state 3. So that's 3000 degrees Rankine, and that's given to me. And then state 4, I can use an isentropic relationship between states 3 and 4 because I have an isentropic process. And I know that V3 and V2 are equal to one another, and V4 and V1 are equal to one another. And then V2 and V2 over V1 is equal to 1 over R. So I'm just plugging in numbers and I get temperature for T4. So as long as you plug in the temperatures as absolute temperature units, everything's going to be just fine. So now it's time to plug in the numbers and calculate what I needed to find for A, B, and C. So my work net out, if I plug in all the numbers, there we go. That's what it boils down to. 168.51 BTU per pound mass. And then my thermal efficiency, if I plug everything in, there's not really any unit conversions that I need to worry about. I've got 51.16%. Sounds good. And the mean effective pressure I do need to be really, really careful about. So if you look at what we plugged in there are a few conversions. So I needed to reconcile the units for BTU. I also needed to reconcile the inches and the feet. So just you need to make sure that all your units are canceling out so that you get the units that you actually want. So I've got 81.83 pound-force per inch squared. So, all right. Well, I hope that was helpful. Thank you very much for watching.